Good morning, gentle folk. My markers are all dead and I'm out of paper for the doc cam, so give me a minute to scrounge. I will be right back. Good morning. Give me 1 second to fire up the document camera here. Today is finally payday, so I will have some fresh markers starting tomorrow. And interim, have a little bit of so we'll make it go with this. Yeah. Make sure things are recording as they ought to. Happy tax day. Well, I guess this year this is not tax day because of the extension due to COVID-19. Today we're going to talk a little bit more about parametric curves. In particular, today I'm going to show you how to do calculus with parametric curves. And what I mean by that is slopes of tangents, right? First derivative stuff. We're also going to talk a little bit about areas. We could talk about second derivative stuff if we wanted to, but I'd be happy if we can keep it focused and basic. I don't see any reason to make this harder than it needs to be. The second derivative stuff doesn't bring any new insight, but it does come with a lot of gnarly formulas. So I think as long as we can get to a place where we are fairly comfortable with the first derivative stuff, then I will be quite happy. So maybe I have a parametric curve that looks like this. Its initial point is down here. If the parametric curves are x of t comma y of t, and the t range is a to b, this would be x of a comma y of a, and the terminal point over here would be x of b comma y of b. So this is a parametric curve. X equals x of t, y equals y of t, and a is less than or equal to t is less than or equal to b. It has an orientation like this. So I can think of this as being a path that's walked by a little ant running around the xy plane. He starts at the initial point and he ends at the terminal point, and he walks along this path in the direction of the arrows as time t runs from A to B. Simple enough, right? We could get this graph just by plotting a bunch of points, right, by making a table, or if we're especially lucky, maybe we get a graph like this by eliminating the parameter t and recognizing the Cartesian equation as something that we know. Here I'm just drawing like a random curve. The main idea to solving the tangent problem, to solving the slope problem in parametric curves, is finding dy dx, right? So I don't have a relationship between y and x normally. Normally I just have a relationship between x and t and a relationship between y and t. And normally to find dy dx, the whole trick is to think about the relationship between y and x, right? You write y as a function of x and then you differentiate. Or you take the equation that relates y to x, if there's just one of, just an equation that relates them rather than a function relationship, and you differentiate implicitly and you solve for dy dx. But here we don't have either of those things. So how do we do this without an equation relating x to y? That's the challenge. And the basic idea is this. I can find instead, because I do have a relationship between x and t, and I do have a relationship between y and t, instead of looking right away for the slope, I could look for how fast the curve is changing in the x direction. So where's a good place to draw this in here? Yeah, we'll do it down here. I could look for how fast x is changing, the point is changing in the x direction, and how fast the point is changing in the y direction. And I could use that to find my slope. In other words, if this down here is like delta x, and this right here is delta y, so I have a little change in y and a little change in x, then out of those two, I could get dy dx. I could get the slope of the curve. That's the basic idea. And the way this ends up dropping out is really nice. If dy dt exists, let me say it like this, dy dt and dx dt both exist, and dx dt is not equal to 0, then dy dx, the normal slope of your tangent line, normal derivative, dy dx, is equal to dy dt divided by dx dt. So you have the relationships between x and t and between y and t. Those are your two parametric curves. You can differentiate each of those with respect to time. And then if you take the y derivative with respect to time and divide it by the x derivative with respect to time, then you'll get dy dx as a function of time. And that's important to remember. So some of the things that we're going to end up looking for will be places where you have vertical tangents or horizontal tangents. For example, here, this horizontal tangent, maybe this is at the point x of c, comma, y of c, meaning that horizontal tangent occurs when t is equal to c. Then dy dx evaluated at t equals c would have to be 0, which means dy dt evaluated at t equals c equals 0. And also that dx dt is non-zero. Okay, so take a look at this formula and then take a look at what we're saying above and see if you can make sense of it. Dy dx, the slope of the tangent line to this curve, is equal to dy dt divided by dx dt. But since x and y are both given as functions of time, hence the dt derivatives here, this guy is going to be given as a function of time. So if you wanted to come back here and find horizontal tangent lines, that would mean finding places where dy dx is equal to 0. Since dy dx is dy dt divided by dx dt, that means finding places where the numerator dy dt is equal to 0, but the denominator dx dt is non-zero, right? Because those are the sort of fractions which turn out to be 0, fractions where the top is 0 and the bottom isn't. So to recap, the slope of the tangent line to the parametric curve over here, x equals x of t, y equals y of t, at a point x of c, comma, y of c on the curve is given by dy dx evaluated at t equals c, which is equal to, and then we have some special notation here. I'll write it out here and then I'll give you the special notation. It's dy dt evaluated at c divided by dx dt evaluated at c. But this notation is so cumbersome, right? This notation for here's the derivative evaluated at this point. When we were talking about power series, we never used notation like that. We used the prime notation, yeah? The prime notation here doesn't work so well because it doesn't tell me what you're differentiating with respect to. Here this says differentiate y with respect to x. Here this says differentiate y with respect to t. Here this says differentiate x with respect to t. So if I just wrote y prime or x prime or something like that, it wouldn't be clear. For example, y prime, am I talking about this derivative or this derivative? But the special notation for dy dt, we write y dot. And for dx dt, we write x dot. This notation comes from physics. The centered dot representing the time derivative. 2 dots would mean the second derivative, 3 dots would mean the third derivative. And so if I come back to this formula here, this is just y dot of c over x dot of c. Much nicer, right? So this is how I remember it. dy dx is y dot over x dot. And if I want to know the slope of the tangent line to the parametric curve x of t comma y of t at the point x of c comma y of c, then I take y dot over x dot and I plug in c. That's all. That's all. So let's take an example. We can make it something a little bit fun, something a little non-obvious. Yeah, okay, so let's find the equation to the tangent line, or of the tangent line. To y equals, oh, sorry, x equals t squared minus t, y equals t squared plus t plus 1, at the point 0, comma 3. So they give me a point on the curve and the equation of the tangent, or the parametric equation, and they want me to find the equation of the tangent line. The big idea is that to get the slope of the tangent line, dy dx, I need to cook up dy dt and dx dt, right? I need to cook up y dot and x dot. I also need to know what time t corresponds to this point. One of the trickier things about getting comfy in the parametric setting is divorcing in your brain the idea of either of these coordinates and the variable t. Your input variable is no longer either of these. Your input variable is time. If we want to, we can take a look at this curve. Let's let t run out to like 4, something like this. All right, so here's a piece of this curve. Here's the point 0, comma 3, but I don't know what time value is associated with that point right now. Right? I don't know what t value I'm going to be plugging in. It looks like the slope of the tangent line there should be large, positive. Let's find out. So first I need to calculate y dot and x dot. Y dot is dy dt, so I take the equation for y and I differentiate with respect to t. I get 2t plus 1. Right? T squared differentiates to 2t, t differentiates to 1, 1 differentiates to 0. X dot is dx dt. So I take this guy, and he differentiates to 2t minus 1. So dy dx is y dot over x dot is 2t plus 1 over 2t minus 1. So if I wanted to find the slope to the tangent line at any time t, I would plug that time in here. Come back to this. If I wanted to find the slope to the tangent line at any time t, I would plug that time t in here. But I wasn't given a time, I was given a point. So I need to find out what time that point corresponds to. So at the point, 0, 3, x of t is equal to 0 and y of t is equal to 3. So for what value of t is x of t equal to 0 and y of t equal to 3? This means, so x of t equals 0 means t squared minus t equals 0, and y of t equals 3 means t squared plus t plus 1 equals 3. So this is a nonlinear system, and solving a system like this could be difficult, but this one is not difficult. T squared minus t equals 0 means either t is 0 or 1. And if t is equal to 0, then t squared plus t plus 1 is equal to 1, which is not 3. So we know t equals 1 is the guy that works here. Everybody follow that? So the time t associated with the point 0, 3 is t equals 1. Thus, the slope of the tangent line at 0, 3 is dy dx evaluated at t equals 1, which is y dot of 1 over x dot of 1, which is 2 times 1 plus 1 over 2 times 1 minus 1 is 3 over 1, or 3. Finally then, this is the slope of my tangent line, right? And the tangent line has to go through this point. So the tangent line is y minus 3 equals, so it's y minus y naught. I'm using the point slope form of a line, equals 3 times x minus 0, or y equals 3x plus 3. And I can come back to my Desmos and see if that looks right. Let's see. Boom, there it is. Looks perfect. Definitely looks like the tangent line to the red curve at that point. So let's take a second think about this example, make sure you've got it clear in your notes, and let me know if you have any questions about the notation or the calculation, finding the time associated with the point, any of those things. What are we thinking? What are we feeling?
So when you're finding t, you said in this case it would be easy. Like, what do you do if it's like a complicated one? I guess, did you kind of just logically figure out the t is equal to 1?
Well, so the first equation here, x of t, my x variable is only going to be 0 if t is 0 or 1. It has to be one of these from the first equation. And then I looked at these two and I asked, well, which one would make this guy true also? T equals 0 makes t squared plus t plus 1 equal to 1, which isn't 3. But t equals 1 makes t squared plus t plus 1 equal to 1 plus 1 plus 1 is 3. So the first equation gave me these two possibilities, and then I just checked each in the second. I won't give you problems where that part is difficult, because that really has so little to do with what we're trying to do here, right? It's just kind of a side thing that we had to do to find the appropriate time. The majority of the work, and definitely the work that I'm trying to test, is whether you understand where the first derivative with respect to x comes from when you don't have an equation relating x to y. So the big deal here is that dy dx is y dot over x dot. And then the only other kind of catch is that you have to remember that those are functions of t. So sometimes I'll tell you, find me the slope of the tangent line when t is equal to 5, and you won't even have to go through anything like this. Sometimes I might ask for the slope of the tangent line at a certain point, and then you'll have to go through something like this, but it will never be any harder than this. The process of finding the time is not something I'm especially interested in beating you guys up on.
Okay.
So, other questions on this?
How did you end up getting 3x plus 3?
So I used my point slope form here. This is y minus y0 equals m times x minus x0. And I plugged in the point 0, comma 3 for x0, comma y0. So I plugged in 0 for x naught, 3 for y naught, and then 3 for m also, because that was the slope of my tangent line. And then I just took this and I simplified, right? So y minus 3 equals 3 times x minus 0. Well, x minus 0, that's just x. So this is y minus 3 equals 3x. And then I added 3 over. So I just simplified this line.
Okay.
Other questions? Yeah.
So all of this work, we're just finding m, the slope, or yeah.
Yep.
Okay.
Yeah, just like in Calc 1, all the work of finding the tangent line is finding the slope. You know, after you have the slope, we just plug into the point slope formula for a line. Any other thoughts or questions on this one? Mostly good? So there is one other calculus operation that I'm very interested in the setting of parametric curves. But before we get to that, I want to kind of recap first derivative stuff with parametric curves. To find equation of tangent line, you need to find the slope of the tangent line, which is going to come from dy dx, evaluated somewhere, right? Which is y dot over x dot, and you're going to evaluate evaluate at the appropriate t value, then plug into point slope. There's two other things that we like to do a lot with first derivatives that you may remember from Calc 1. We like to find maxes and mins, right? And then we also like to find places where the curve is vertical. So we want to find horizontal and vertical tangent lines. That's what I'm getting at. To find horizontal tangents, find places where dy dx is equal to 0, which will come from y dot equaling 0 and x dot being non-zero, right? If I want y dot over x dot to be equal to 0, that means I need the top to be 0, but I need the bottom to not be 0. And then vertical tangents, we want to find places where dy dx blows up to plus or minus infinity. Right? Remember, we can think of a vertical line as being a line with infinite slope. And in this setting, that is the nicest way to think of it. And these will come from y dot being non-zero and x dot being equal to 0. So if you're asked to find vertical and horizontal tangents, the thing to do is to calculate dy dx. It's y dot over x dot. You need it for both. To find places where you have horizontal tangent lines, find where the top of dy dx is equal to 0. And to find places where you have vertical tangent lines, find where the bottom of dy dx is equal to 0. Those are going to be t values, because these are going to be functions of time. So after you find those t values, don't forget to plug them back in to x of t and y of t to get the actual point. Right? If I ask you where is there a horizontal tangent line on this graph, I want to know what is the ordered pair x comma y where the tangent is horizontal. I don't want a time. And there's a bunch of problems in your current homework that are going to ask you for horizontal or vertical tangents. And it's important that you pay attention to how the question is being asked. Do they ask for what value of t is the tangent horizontal? Or do they ask at what point x comma y is the tangent horizontal? If they ask for a point, make sure you go back and plug those t values in to the original parametric equations to find the point. So this stuff is all, I think, very easy. It's all conceptually things that you've done before from early Calc 1, just in a slightly newer setting where you've got some different calculations to do. And the curves can be a little bit cooler looking here because they don't have to have one coordinate a function of the other. But there is one other calculus operation that's very interesting in this setting, and that is arc length. So if we have time, I would like to introduce that, and we do. So the other cool calculus thing we're going to do with parametric curves is talk about arc length. So maybe I have a parametric curve here. Starting point, ending point. I would like to know what is the total length of this curve. If I think of this curve as like a rope, and I wanted to stretch, like pick this rope up off the page and stretch it out and measure how long it is. How can I do that? It's not a simple thing. And mathematically, it's not as clear as it might seem to be at first. The trick is to chop it up into a bunch of little pieces and then apply the Pythagorean theorem. So just like before, if I call this delta x and I call this delta y, then this little right triangle actually does a really good job of approximating the length of the curve from this point to this point. And in the limit, as delta x goes to 0, it would become exact. So if I call this length up here, S is the symbol we always use for arc length. So if I call this guy delta S, then by Pythagoras, delta S squared is delta x squared plus delta y squared. Which means delta S is the square root of delta x squared plus delta y squared. And then if I multiply top and bottom by delta t over here, then delta S is this guy, delta t over delta t. The delta t downstairs there, I'm going to move him inside the square root as delta t squared. And so this becomes the square root of delta x squared over delta t squared plus delta y squared over delta t squared. And then I still have one delta t hanging out on the ass end. That's the one from the top.
Wait, what are we doing with the delta t's?
So delta t, I divided top and bottom by delta t. I multiplied by delta t over delta t. And then the delta t that was on the top stayed outside. The delta t that was on the bottom came inside the square root as 1 over delta t squared. So this guy down here I treat as the square root of delta t squared. And then I'm able to shove him into the square root.
Okay.
So we end up with this formula. Delta S equals the square root of delta x over delta t all squared plus delta y over delta t all squared times delta t over 1 left outside from the numerator. And as delta t goes to 0, in the limit, this becomes the differential statement ds equals the square root of dx dt squared plus dy dt squared times dt. If you like, you can write that in the dot notation, and that's how I like to write it. This is x dot squared plus y dot squared dt. And all of this is equal to ds. So finally, s, my arc length, is the integral of ds, is the integral of the square root of x dot squared plus y dot squared dt. And so the length of the parametric curve x of t comma y of t from t equals a to t equals b is the integral from a to b of ds, which is the integral from a to b of the square root of x dot squared plus y dot squared dt. So this is our formula to find the length of a parametric curve. In fact, this is a formula that will work to find the length of any graph, because if I give you a curve that is not already parametric, you can parametrize that curve. You can put that curve into parametric form and then apply this formula. So the last thing I'd like to do today, if we have time, is to do one example of an arc length calculation to show you what these can look like. Where's my phone? Yeah, we got time. Unfortunately, these integrals tend to be tough. You know, you see the square root of some stuff squared there, that kind of looks trig subby. And oftentimes these integrals are trig subby. So let me see if I can find one that comes out real nice. Yeah. So let's see if we can find the length of the parametric curve x of t equals cos t, y of t equals sine t, from t equals 0 to t equals 2 pi. This is a curve we've seen before. This gives the unit circle. So I know what this should turn out to be, right? What's the circumference, or what is the length of the arc all the way around the unit circle? It's the circumference of the unit circle. So it should be 2 pi. Let's see what we actually get. I always like to calculate ds. It's x dot squared plus y dot squared. So what is x dot? Well, it's the derivative of cosine. So this is negative sine t all squared plus, and then y dot is the derivative of sine. That's cos t all squared. And there should be a dt here, sorry. So that's sine squared t plus cos squared t dt. So in other words, ds, sine squared t plus cos squared t is 1, is just dt. So s is the integral from a to b of ds, which is the integral from 0 to 2 pi, because that's where I was asked to find the length, from t equals 0 to t equals 2 pi, of sine squared t plus cos squared t dt, which is the integral from 0 to 2 pi of 1 dt, which is just 2 pi. So at least for the unit circle, this works nicely. This needs to be under a square root, sorry. Square root of this, square root of this, square root of this, square root of this. But the square root of that is still just the square root of 1, which is 1. So the integral here really is just 2 pi. So practicing with this arc length formula is something that can get a little bit gnarly. I don't think I dropped any of these problems in your WebAssign right away, but I might add just one at the end here for you to play with. Like I said, sometimes these integrals can be really brutal, and it's not my intention here to brutalize you guys. Let's see, did I put one in? Usually on the first parametric homework, I just have one or two, but I think I pulled them out for you guys because things are a little crazy right now. The other calculus operations that we're going to talk about when it comes to parametric curves, besides arc length and the tangent line, I don't usually talk about the second derivative. Like I said, that's just more formula stuff, and there's no real new intuition or anything beautiful there. But it is worthwhile to talk a little bit about the area problem because it will help give you some insight into why areas in the regular sense work the way they do. So yeah, I give you one area problem and some tangent problems. So I am going to go ahead and add an arc length problem or two, but we won't add any second derivative stuff. Any questions on the examples that we worked here today? Or on these formulas? Okay, then I think that's where we're going to end the lecture for today. Do take a look at the Patrick JMT and Paul's online note stuff that I posted if you get stuck anywhere in the homework. Also, feel free to send me questions via email or Canvas. All of those are good resources. Next week, we're going to talk a little bit about polar curves, which is something that you've probably seen a little bit of back in trigonometry, but I want to look at them anew and then solve some fun problems with them. Integral represents the length of the curve. Yeah, and the exact length of the curve. Okay, 1, 2, 3 of these. That will be good. Okay, so I tossed in just a couple of arc length problems to your current homework set. Keep working on those. If you get stuck on anything, don't be shy about asking for help. You can message me on Canvas and I will get back to you as quickly as I can. You can also come by my office hours, Tuesdays and Thursdays, 9 to 11. The link is in Canvas, right there on the main page, on the home page, also on the syllabus page. And then tomorrow we will solve a few more challenging arc length problems. And I'll explain how the area problem works in the setting of parametric equations. And then the following week, we will talk about polar curves, where the really only interesting calculus operation there is the area problem. Tangent problems in the polar setting are not super exciting, but the area problem is, because a lot of stuff that is actually really hard to do in Cartesian coordinates becomes much, much nicer in polar coordinates. So please work on the parametric curves homework. If you get stuck, ask for help. Let's get this knocked out. And then next week, we will talk about polar coordinates. At the end of next week, I will give you your last test, test 3, which is going to be a take-home test based on the things that we've been doing lately. So it'll be on Taylor series and Taylor polynomials, a big scary formula for power series, and then these kind of geometric things we've been doing the last few days, parametric curves and then polar coordinates. So stay in front of that wave. You're almost done. You've almost made it through Calc 2. You're definitely done with the hard part. Hang in there. if you're feeling like you're behind or you're in trouble, you're worried about the final, anything like that, now is a good time to start talking to me about that so we can start preparing. And then at the end of next week, I will give you your last midterm. Our final exam is going to be on the same day and time it is in the syllabus. Nothing is going to change there except that the test is going to take place online. We are going to use HonorLock probably for that test, and I will set up a practice quiz in Canvas so you can test out HonorLock. I will get you the tokens. You won't have to pay for anything, but you will need access to a webcam. If you don't have access to a webcam, talk to me sometime before the final and we'll set up an exemption for you. But please, if you do have access to one, even if you don't have one on your laptop or whatever, if you've got someone in the household who has one or something like that, try to get access to one. Things will go more smoothly that way. But if you can't, just let me know. We'll make it work. Any questions about what we're doing or where we're going or how we're going to get there?
I got a question real quick about them. You said you posted some outside resources, but I'm not really sure where to find them.
Let me take a look and make sure those are where they should be. I think I posted them for you guys under announcements, but for my other classes, I posted them under modules. So maybe I should move those to modules. Oh no, I didn't post them under announcements for you guys. So I must have just never added them to your modules. I suck. Okay, here, I will move those from my other classes modules into your modules. So look.
It's just, I don't see modules like on our tab list.
Refresh the page, you'll see it now.
Oh, yep. There you go.
Okay, so yeah, I did this for my other class, but I guess I never got around to moving it over to your class. So I will go ahead and do that right now.
Because now I see parametric curve resources, but there's nothing underneath it, I guess.
Yeah, it's just taking a second for me to get things copied over.
Okay, all right.
But yep, they'll be right there. Any other questions, folks? All right, then that is where we will leave it for today. And like I said, if you do run into any questions, check out Paul's online notes, check out Patrick JMT, but don't be shy about asking me either. If you would prefer to just message me right away, that's fine. I will get back to you as quickly as I humanly can.
Before you end the session, could you just show your notes one last time, that last example? We're finding the length.
Yeah, of course, here. So I took the formula I had for the arc length in terms of this integral. I need x dot squared and y dot squared. So x is cos t. So x dot is negative sine t. So x dot squared is negative sine t all squared. I need y dot. Y is sine t. So y dot is cos t. So y dot squared is cos t all squared. And then ds is the square root of x dot squared plus y dot squared is the square root of negative sine t squared plus cos t squared. And then sine t squared plus cos t squared, that's just 1. So this is the square root of 1 that I need to integrate. And if I integrate 1 from 0 to 2 pi, I get 2 pi.
All right, got it. Thank you.
Yeah, of course, no problem. Have a nice rest of your morning, guys.